Hey everyone, I thought we could do some calculus today. Let's take a look at some calculus. So yesterday I mentioned that there existed this thing called the mean value theorem. Do you remember what its preconditions were? Because you're going to need them on the AP exam. All right, remember this said that if f is continuous on the closed interval from a to b, and there's a second precondition, differentiable, we can take the derivative everywhere, on the open interval from a to b. We're not concerned about endpoints, no derivatives at endpoints, just on the interior of the function. Okay, if these two things are true, then we have a conclusion. Now, in the last 2 years, AP has made a push where students need to talk about or use these preconditions. So you're going to really need to be responsible for the preconditions here with MVT, mean value theorem, also with IVT, remember the fists in the air, the intermediate value theorem, less so with EVT, but we do need to know these two golden, okay? So let's move on. Then what's true? Well, then if these things, then there must exist a point x equals c, at least one point x equals c, such that f prime at c is equal to the average rate of change, f of b minus f of a over b minus a. So the slope at a point is equal to the slope of the secant between 2 points. The average rate of change is equal to the instantaneous rate of change. That's what we know. There must exist at least 1 point x equals c such that this is true. Now, it may be the case that there's more than 1 point. So, for example, if I have this function, here's the slope from a to b. Do you see any places where the slope of f of x would be the same as the slope of this line, i.e. parallel to this line? Well, it looks like I'd see something over here, and it looks like I'd see something over here. Okay, so I'm guaranteed at least 1 point will exist, but there could be more. When is this true? If this function is continuous on the closed interval, so let's go back and look at these preconditions. Is this function continuous on the closed interval from here to here? Yes. I don't see any vertical asymptotes. I don't see any jump discontinuities. There's no holes. There's no oscillating things. This function is continuous on the closed interval. Now, what about differentiable? Can we take the derivative at every point here? We sure can. There's no point along here where we can't take the derivative between a and b. So we've met the preconditions, which means there must exist at least 1 point where the slope of the secant from a to b is the same as the slope of the curve. In this problem, we actually get 2 such places. Now, remember what our textbook said. The mean value theorem is an existence theorem. It tells us that this point exists. It doesn't really tell us how to find the point. We can sometimes, what did the book say? Sometimes satisfy our curiosity about the location of C. And that's what we're going to do today. We're going to figure out what, where these x equals c's show up. Okay? So let's start with this basic homework question and AP question. We're given f of x equals square root of 1 minus x squared on negative 1 to 1. Okay? Now, hopefully you know what this function looks like. You don't make that face. This is a semicircle. It's only the top half of the semicircle. The radius of this semicircle is 1, and this semicircle is centered at the origin. Okay? So graphically, I know I'm looking at this situation. And I'm looking from negative 1 to 1. Okay. So, is f of x continuous? Well, yeah, f of x is continuous on this domain. If I try and plug in a 2 here, 1 minus 4 is negative 3. That's not going to be so good for a square root. If I plug in a negative 3 here, negative 3 times negative 3 is 9. 1 minus 9, I get negative 8. That's no good either. So this is, in fact, my domain. And we can see that here on the graph, that the whole graph exists from x equals negative 1 to x equals 1. But let's ask this question. Is this function continuous on negative 1 to 1? Because that's what the mean value theorem is concerned about. And I say yes. Okay, part A. Show that f of x satisfies the preconditions of MVT. Okay, now this showing, it's really kind of easy because it's almost always going to be true, especially if they're saying show it. We just have to kind of know it and state it. So what were the preconditions? 1, f is, and you can underline it to say, no, really, it is continuous on negative 1 to 1. Okay? So, negative 1 to 1, yes, we are continuous. B, 2. What about differentiable? Remember, f is differentiable on not the closed interval, but the open interval. So, what are we going to do here? Well, I think we need to take the derivative of this. And my recommendation is that you ditch that radical and you turn this into 1 minus x squared to the 1/2 power. That's going to be a pretty easy derivative with our chain rule. We'll bring down that 1/2 and we'll see that f prime is 1/2. Leave the inside alone. Subtract 1. Now times the derivative of the inside function. The derivative of this is 0, and the derivative of negative x squared is minus 2x. Okay? Hey, look, and this 2 can cancel. And so I end up with f prime of x equals x over square root of 1 minus x squared, right? Because this is square root, and this says go to the bottom, and there's the stuff under the radical. So here's our f prime, and now what do we know about f prime? Well, I've got something in a denominator. And we remember learning in pre-cal that I can't have a 0 down here. And when would I have a 0 down here? Well, if x were equal to 1, then 1 minus 1 would be 0. The derivative is undefined at x equals 1 and x equals negative 1. Oh no, does that mean we don't meet the precondition? Because we're not differentiable at 1 or negative 1? No, because look, f is differentiable on negative 1 to 1, not including the endpoints. Yay! So, then I could say, yes, f is differentiable, okay? Now, I will say that sometimes you'll run into a problem where even though you don't meet the preconditions, like the function isn't differentiable, we can still find a place x equals c. We're just not guaranteed we're going to find a place. That's the cool thing about MVT is, or a cool thing about MVT is, that we're guaranteed at least one place x equals c where the slope of the secant equals the slope of the tangent. When we don't meet the preconditions, that could still happen. We're just not guaranteed that that's going to happen. Okay? So, part A, show that f of x satisfies the preconditions, f is continuous on -1 to 1 closed interval, f is differentiable on -1 to 1 open interval. Well, fabulous. All right. So what's question part B then? Well, part B is going to say if f of x equals square root of 1 minus x squared on -1 to 1, find that c. Part B. Find c that satisfies MVT. Okay, now a lot of people have difficulty with this part, and it's not really hard because remember we're looking for an x value. X equals c. And remember what the mean value theorem says. It says the derivative at a point is equal to f of b minus f of a over b minus a. Okay, so let's find that derivative. Oh, we already did. And over here, we're going to do f of 1 minus f of -1 over 1 minus a -1. So when I plug a 1 in here, well, 1 minus 1 is 0, and the square root of 0 is 0. And if I plug a -1 in here, well, -1 squared is 1, and 1 minus 1 is 0, and the square root of 0 is 0, over 2. And so we end up with 0. So this derivative is equal to 0. Okay, square root 1 minus x squared equals 0. Please don't freak out by that fraction. Remember, I started teaching way back in pre-cal that if you just multiply by this common denominator on both sides, the fractions will go away, and look over here, 0 times stuff is 0. There. So, when x equals 0, MVT is satisfied. Mr. Kukla, there were no C's. Yes, see, this is what we're looking for. We're looking for the specific x value where the slope or derivative is equal to the average rate of change. So here's our average rate of change, and I want to know when my derivative is equal to that average rate of change. When we solved that equation, we found out that only occurs at x equals 0. Ta-da! MVT is satisfied when x equals 0. And think about this again graphically. When we look at this graphically, what's the average rate of change from -1 to 1? Well, that slope is 0. You see any other places where the slope is 0 here? Looks like the slope is 0 is here, also at x equals 0. So that's what the mean value theorem is looking for. It's looking for places where the slope of the tangent would be equal to the slope of the secant, where the average rate of change is equal to the instantaneous rate of change. Okay? All right, so we're going to do a couple problems practicing this, and then I'd like to actually go back and talk a lot more about what we were doing yesterday, and we also have a tale of 2 second derivatives to talk about. So let's go. How about f of x equals x to the third minus 9x plus 1 on 0 to 1. Well, do we meet the preconditions for mean value theorem? Well, this is a polynomial function, and polynomial functions are continuous everywhere. So we've got that part done. But what about differentiable everywhere? Well, f prime of x is going to be 3x squared minus 9. Is this parabola? Does this exist everywhere? Can I plug numbers, any number I want into this between 0 and 1? Sure can. This is differentiable on the open interval. This is continuous on the closed interval. Differentiable on 0 to 1, continuous on closed interval 0 to 1. So we know we've met the two preconditions for mean value theorem. Let's now actually use mean value theorem. Remember, f prime of c equals f of b minus f of a over b minus a. In our problem, the derivative, 3x squared minus 9, will equal, we're plugging 1 into the original function. This is f of 1 minus f of 0 over 1 minus 0. Well, f of 1 is 1 minus 9 is negative 8 plus 1 is negative 7. And f of 0 is 1 over 1 minus 0. So we get negative 8. All right, so we want to solve this equation. X squared minus 9 equals negative 8. We'll add 9 to both sides. We get 3x squared equals 1. We'll divide by 3. We get x squared equals 1/3. And no kidding, there are still calculus students who make this algebra 2 mistake. When I take the square root of both sides in an equation, what do I need to remember? That's right, I need to remember the plus or minus. You need to remember that plus and minus. If you don't, you're going to be a sad puppy. So x equals plus and minus square root of 1/3, which is also because if this were multiple choice, you would not see that answer. You'd see square root of 1 over square root of 3. No, not that answer. They would rationalize, and you would see plus and minus root 3 over 3. So it turns out that our third degree polynomial has two such places where the slope of the secant is the same as the slope of the tangent. Let's take a look at that. So if we've got x to the third minus 9x plus 1, and I only need to look from 0 to 1. Scale of 1 should be sufficient. We already know the values are positive 1 and negative 7 for y values. So let's go negative 10 to 5 in steps of 1. What do you mean, Mr. Cuckoo? There's two places where the slope of the secant and the slope of the tangent are the same. Really? Well, so it seems, but wait a second, Mr. Kukla. I only see one place where the tangent line from here to here is the same as the slope of the tangent of the curve. You said there were two. Well, I did say there were two. But take a look at these numbers again. Plus and minus root 1/3. Do both of these exist on this domain? Oh, no, they don't. That one doesn't. And so our answer is only the positive one in this case. Yes, I do need to think when I do math. And in life, thinking is good. Okay, so that's us satisfying our curiosity about finding values of C such that the mean value theorem is satisfied. But I want to go back now and do a little practice with what we really use the mean value theorem for. Remember, mean value theorem says, or a textbook said, we can sometimes satisfy our curiosity about the location or value of x equals c, but the real power of the mean value theorem is in its corollaries. And so we were using these corollaries to talk about how negative 2 to 3. Okay, we were talking about how to use these corollaries to find minimums, maximums, increasing, decreasing, concave up, concave down, and inflection points. Hubba hubba, there's so much stuff to find. I can tell we're in chapter 3 because we're doing a lot of calculus and a lot of algebra. Okay, so let's start with our first derivative. F prime of x equals 3x squared minus 2x minus 8. Okay? And I wonder, when is f prime equal to 0? Well, this factors, I hope, as 2 and 4 and minus and plus. And so I see I get critical numbers at -4/3 and +2. Okay, so I'll make an f prime sign chart with -4/3 and +2. Now remember, this is an up-pointing parabola, so if I sketched that parabola, I would see, oh look, f prime is positive, f prime is negative, f prime is positive. So what do we know about f, because we know f prime is positive? Well, when f prime is greater than 0, f is increasing. And when f prime is less than 0, we know f is decreasing. So we can say f is increasing on -∞ to -4/3 union 2 to infinity, and we're often going to be asked to justify this because f prime is greater than 0 on these intervals. Okay, f is decreasing on -4/3 to 2 because f prime is less than 0 on this interval. So there's increasing and decreasing. Now, what about maxes and mins? Well, let's take a look at maxes and mins. So we remember when f goes from increasing to decreasing, we have a max. Well, in f prime land, increasing f means f prime is positive. So when f prime goes from positive to f is decreasing, so f prime is negative, then we have a min. Okay, so what do I see here? I see f prime going from positive to negative. When f prime goes from positive to negative, we have a max. When f prime goes from positive to negative, we have a min. Why did you write min? We have a max. Okay, so there is a max at x equals -4/3 because, and here's that sentence that you're going to write over and over and over and over and over this year, because to the left of x equals -4/3, f prime is greater than 0, and to the right of x equals -4/3, f prime is less than 0. It's only one sentence. I know it seems wordy, but you have to write it, or else they'll say it's vague. I don't know, because most students say things like to the right it's negative, and to the left it's positive. Well, I don't know what the hell it is in that sentence. So you're going to have, and I don't know to the right and left of what. So you have to be explicit with all this information, and that's why we're going to use our bulletproof justification sentence. So that's my max. Oh, but wait a moment. There's also a min to consider. Okay, so let's think about our min. We know that minimums occur on a function when the function goes from decreasing to increasing. A min occurs when f goes from decreasing to increasing, or when f prime goes from, if f is decreasing, then f prime is negative. If f is increasing, then f prime is positive. So when f prime goes from negative to positive, we have a min. Okay, and I see such a place over here at x equal to 2. So I'm going to say there is a min at x equals 2, because to the left of x equals 2, f prime is less than 0, and to the right of x equals 2, f prime is greater than 0. Great, so we've justified mins and maxes now. We've got a max at negative 4/3 because f prime goes from positive to negative. We've got a min at x equals 2 because f prime goes from negative to positive. And if we only wrote down those minimums and maximums, we'd lose a lot of points on the test, because remember, minimums and maximums can occur in 3 places. Where can minimums and maximums occur? Minimums and maximums can occur, 1, where f prime equals 0. And that's what we did. We set the derivative equal to 0. But they also occur where f prime is undefined. Well, Mr. Kukla, this is a polynomial f prime. This polynomial exists everywhere. There's no f prime undefined. I agree. But what was the third place we could find maxes and mins? Endpoints. Did we check the endpoints? Remember, we're on a domain here. Now, if it had just been this problem, our two answers, x equals negative 4/3 is a max, x equals positive 2 is a min, that would be sufficient. But because we were given a restricted domain for our f of x, we have to consider endpoints as well. All right, so let's see what's happening here. Negative 2 is over here. So what I see is I can't go past negative 2. There's nothing beyond negative 2. But I see that from negative 2, after that moment, f prime is positive, which means the function f is increasing from negative 2. F is increasing after negative 2, which means negative 2 is a min. Okay, so how do I justify that min? I need the special endpoint justification sentences. There is a min at x equals negative 2 because x equals negative 2 is the left endpoint, and to the right of x equals negative 2, f prime is greater than 0. All right, now we have another endpoint over here at 3. And what do I notice happening over here? The function, the derivative of f is positive. So I know f prime is increasing to this point. I know f is increasing to x equals 3. So f is increasing to this point. Well, that means 3 is going to be a maximum. So there is a max at x equals 3 because x equals 3 is the right endpoint, and to the left of x equals 3, f prime is, greater than 0. Okay, so watch out for endpoints. People lose lots of points because, especially on our chapter test, because they don't check endpoints. Please check endpoints. Okay, so are we done? Oh no, we're not done. We haven't yet found inflection points or concave up, concave down. And for that, we need the second derivative. So that's going to be 6x minus 2. Okay. Well, I know that an IP can occur, an inflection point can occur when f double prime changes sign. Okay, I'm looking for when f double prime equals 0 and when f double prime is undefined. Unlike maxes and mins where I also check the endpoint, I can't have an inflection point at an endpoint. All right, here we go. I'm concave down on one side and then I get to the endpoint. Well, I can't be concave up on the other side because there's no other side. So all I have to worry about is f double prime equal to 0 or f double prime undefined. Well, our f double prime is never undefined, but our f double prime is equal to 0 when x equals 1/3, right? So because 0 equals 6x minus 2, and 2 equals 6x, and x equals 1/3. Okay, so I've got this critical number, so I'll make an f double prime sign chart and put my one critical number on my f double prime sign chart, and I'll test on either side of that f double prime sign chart. I'll plug in a 0 and I get -2, and I'll plug in a 1 and I'll get +4. I also could have done this graphically because I know that this is an x-intercept on this graph with a positive slope and a negative y-intercept. So I'd be looking at a graph like that, and lo and behold, f double prime is positive over here and f double prime is negative over here. Okay, so what do we know from this? Well, do you see f double prime going from negative to positive? That tells me there's an inflection point. So there is an inflection point at x equals, on f of x, at x equals 1/3, because to the left of x equals 1/3, f double prime is less than 0, and to the right of x equals 1/3, f double prime is greater than 0. We have to write justification sentences for all maxes, all mins, all inflection points. But what about concave up and concave down? Well, we know, according to the mean value theorem, that when f double prime is greater than 0, f is concave up. And when f double prime is less than 0, f is concave down. So I can say f is concave up on, on 1/3 to 3. Remember, we have that restricted domain because f double prime is greater than 0 on that interval. And f is concave down on -2 to 1/3 because f double prime is less than 0 on that interval. Okay, so that's all the stuff, right? We've talked about mins, maxes, increasing, decreasing, inflection points, concave up and concave down. You need to be able to do that with every function. That's a huge part of our differential calculus. If you think about it, in the age before this object, how would we graph something like this? Well, I can't factor this by grouping. I don't know what its x-intercepts are. And so I'm now turning to calculus to give me all this information. And we'll come back again in a little bit where we just have a function and we find all these things about that function, and then we graph the function based on all these things that we've found out. Okay? Right now, we're still in the information gathering stage, learning how to gather all this information. Where is f double prime greater than 0? Where is f prime less than 0? How do I figure out where there are mins and maxes? Okay? So keep practicing those. Those are really, really important. Finally, today I want to look at a tale of 2 second derivative tests. Okay? So we know that if f of x equals x to the third minus 3x squared plus 2, then f prime would be 3x squared minus 6x, and f double prime would be 6x minus 6. Okay? And we just used that second derivative to say, okay, we've got this critical number at x equals 1, and I know that if I plug in a 0 here, I get a negative, and if I plug in a 2 here, I get a positive. So because of this, we know that f is concave down on negative infinity to 1, and f is concave up on 1 to infinity. We also know there is an inflection point on f at x equals 1 because to the left of x equals 1, f double prime is less than 0, and to the right of x equals 1, f double prime is greater than 0. And that's the way we most often use the second derivative test. We use the second derivative test to determine concavity and inflection points. But wait, there's another second derivative test. A second derivative test, if you will. And that second derivative test, that alternate second derivative test, is use the second derivative to find maxes and mins. What? I thought I used the first derivative for that. Well, normally you do, but sometimes, it's not going to work out so well. So here, for example, I know if I set f prime equal to 0, there are no endpoints to consider here. F prime is never undefined, so I just have to find when f prime is equal to 0. I could find some critical points, 3x, x minus 2. I've got critical points at 2 and 0. And I could make a sign chart. I could plug a 1 into f prime and get negative. I could plug a 3 into f prime. 3 squared, 9, 27 minus 18 is positive. And I could plug a negative 1 in. I get 3 plus, that's also positive. Hey, by the way, the alternating sign thing, it doesn't always happen, so check the intervals. Or think about it graphically. This is an upturned parabola. Positive, negative, positive. Okay, so we know that there's a max over here at x equals 0 because f prime goes from positive to negative. We know over here at x equals 2 there's a minimum because f prime goes from negative to positive. So what's all this about wanting to use the second derivative to find maxes and mins? Well, so I want to say, is there a max or min at x equals 2 on f of x? So here's my f of x. And here's how I want to use the second derivative. I know f prime of 2 equals 0. I already showed that here, right? But what about f double prime of 2? Well, if I plug a 2 in here, 2 times 6 is 12. 12 minus 6 is 6. F double prime of 2 is greater than 0. And what do I know? Because the second derivative is positive, the second derivative is greater than 0. Therefore, f is concave up at that point. So at that point, too, I have a 0 slope, a horizontal tangent, and the function is concave up. Concave up with a horizontal tangent, that tells me I have a min. So I'm going to say, because, and here's my justification sentence when I have to use the second derivative test, there is a min on f at x equals 2 because f prime equals 0 and f double prime is greater than 0. All right? There's my justification sentence for second derivative test. It's a little different than our first derivative test justification sentence for a min. Now, let's check, is there a max or a min at x equals 0? Well, we know that f prime of 0 equals 0. We showed that over here. But what about f double prime of 0? Well, f double prime of 0, if I plug a 0 in here, I get negative 6. So f double prime of 0 is less than 0. So what does this mean f is doing? Well, because f double prime is less than 0, we know that f is concave down. Okay, so I'm drawing concave down. I'm drawing a horizontal tangent. What do I have happening there at x equals 0? I have concave down with horizontal tangent. I've got a max. There is a max at x equals 0 because f prime of 0 equals 0 and f double prime of 0 is less than 0. That's all I have to do to claim that max. Now you may say, well, Mr. Kukla, it's kind of a pain in the butt because, you know, I could have found all that information out just by working with f prime. I now have to take this other derivative and consider the behavior of the other derivative at that point. Yes, that's what this is all about. Why do I need to do that, Mr. Kukla? This is crazy. And I agree. But wait, let's put you in this position. X squared plus y squared equals 9. Okay. Let's take the first derivative, 2x plus 2y dy dx equals 0. Remember, with implicit differentiation, we need to solve for dy dx. So I get 2y dy dx equals negative 2x. And then I divide to get dy dx alone. And I get negative 2x over 2y, or negative x over y. Now, there's the first derivative. Please notice the first derivative has both x's and y's in it. Uh-oh. How am I supposed to determine where I have mins and maxes? You know, conveniently, I know what this thing looks like. But if I put a 2 here and a minus here, that's going to be much harder because we haven't been practicing any hyperbolas. So, what is this going to look like? Okay. I can figure out at x equals 0. I have some critical points, right? Because dy dx equals 0 when, well, let's set this equal to 0 and multiply both sides by y. We get negative x equals 0, and so x equals 0. So I know I have a critical point at x equals 0. All right, so let's go from there. Negative x over y. But I'm supposed to plug in values on either side of x equals 0. And here's the thing. I don't know what the y values are. I only know the x values. And since we actually know what this graph looks like, damn, it's got a max and a min at x equals 0. And so we really can't use our original first derivative test for maxes and mins here. Whenever I find myself having to do implicit differentiation, I always use the second derivative test. Okay? Let's show how that works. At x equals 0, what's happening? Okay, so at x equals 0, I need f double prime, right? I have to plug this into f double prime. So here's f prime. I need to find f double prime, which means I need to take the derivative of this, which means I need to use the quotient rule. So low d high minus high d low. The derivative of y is called dy dx over low squared. Remember, we have to replace this dy dx with what dy dx is equal to. All right? So this is now going to be dy dx equals negative x over y, and our second derivative is going to be negative y plus x times minus x over y squared. All right, so I'm going to tidy this up just a little bit more, and I'm going to have negative y minus x squared over y squared. And I want to plug in x equal to 0. Okay, well, let's plug in x equal to 0. I get this dx2 equals negative y minus 0 over y squared, which is negative 1 over y. So the second derivative depends on this. All right, well, this is a little trickier. We know x equals 0. Okay, so our original equation, x squared plus y squared equals 9. So if x equals 0, then y squared is 9, and y equals plus or minus 3. So I've got these two y values to consider. I've got two ordered pairs. I've got 0, positive 3. I've got 0, negative 3 to consider. Well, if I put my positive 3 in here, I see negative 1 over 3. So at this point, the first derivative equals 0, and the second derivative is less than 0. So that means I have a max there, right? Second derivative less than 0 means the function is concave down, and I have a horizontal tangent, so I've got a max at this point. But we also had this ordered pair, so what if we plugged in a negative 3 here? Then minus a minus would be positive 1/3. So we know that dy dx equals 0, and we also know that the second derivative would be greater than 0. And therefore we have a min at x equals, at 0, negative 3. All right, so I can figure out maxes and mins using the second derivative test. You will need to know the second derivative test. Okay. Let's take a look at the time. The time is 47 minutes. Let's get in one more practice problem. Okay. How about show that f of x equals sine squared x on 0 to 2 pi has a min at x equals pi. Okay? All right, so first derivative test for finding a min, I need f prime equal to 0, or f prime undefined, or endpoints of a bounded interval. So I want to check my endpoints, and let's take a look at this f prime. F prime is going to be, because remember, f is sine x being squared. So 2, leave the inside function alone, times the derivative of the inside function. So there's my f prime. When does f prime equal to 0? When sine equals 0, and when cosine equals 0. So sine equals 0 at x equals 0, pi, and 2 pi. Cosine equals 0 at x equals pi over 2 and 3 pi over 2. And that's why we spent so much time talking about this last year in trig. Even in August we reviewed this stuff because we need to be really comfortable with this. Okay, so I've got this big honkin' f prime sine chart from 0 to 2 pi. And and 3 pi over 2. Okay, these are all critical points, so I need to plug some values in to f prime, right? This is an f prime sign chart. I like plugging in pi over 4s, 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So sine of pi over 4 is positive root 2 over 2. Cosine of pi over 4 is positive root 2 over 2. So positive times positive is a positive. But at 3 pi over 4, the cosine will be negative. The sine will be still positive. So I have negative times positive, which is negative. If I put in 5 pi over 4, both sine and cosine are negative here. So negative times a positive is a positive. And if I put in 7 pi over 4, cosine is positive, but sine is negative, so positive times negative is negative, times a positive is negative. And so I can see that I have a min here at x equals pi. And my justification sentence would be, there is a min at x equals pi because to the on f of x. Because to the left of x equals pi, f prime is less than 0, and to the right of x equals pi, f prime is greater than 0. Okie doke. So that's a way we can show that there's a min at x equals pi. Now, is that the only min? Well, no. There's actually two others. Look here. From x equals 0, f prime is positive, which means f from that point would be increasing. Or increasing, or increasing. I just know f is going up. So, what does that tell me about x equals 0? Well, x equals 0 is the lowest point in that neighborhood because everything goes up from there. So I know that x equals 0 is also going to be a min. Okay, what about over here? Well, over here I see f prime is negative, which means f is decreasing. And since f is decreasing to that point at 2 pi, I know that f is going to have a minimum over here at 2 pi. So there are minimums at 0, pi, and 2 pi, but they only asked us about the one at pi, so that's the only one I need to talk about here. Okay. What about this one? Let's do one last problem. F of x equals 2x plus cosine x. And why don't we ask questions like max, min, increasing, decreasing, concave up, concave down, inflection points. Okay? So, I start off 2 plus cosine x. When's that equal to 0? Well, so I got a problem here because cosine is never equal to -2, which means there are no critical points. There are no places where this derivative is equal to 0. Is this derivative ever undefined? Well, no, cosine is defined everywhere, and just because I shifted it up 2 doesn't mean the function doesn't exist anymore. Oh. Are there endpoints? No. Oh. So, here's my f prime sign chart. There are no critical numbers on it. I can plug any number I want in to f prime. So here's f prime, okay? And I plug a number in, like 0. What happens? 0, cosine of 0 is 1. 1 plus 2 is 3. That's positive. In fact, we know graphically that this graph has been shifted up 2, and this graph is always above the x-axis. Our f prime is always positive. We call that a monotonic function. It only has one behavior, either increasing or decreasing. This function is always increasing. Okay, well, can I say more about this function? This function is always increasing. This function is never decreasing. This function doesn't have any maxes or mins. What about inflection points in concavity? Well, for that, we turn to f double prime. The derivative of 2 plus cosine x will be minus sine x. Oh, when is minus sine x equal to 0? Well, minus sine x is equal to 0, is equal to 0 when sine x equals 0, and that happens at x equals 0, pi, 2 pi, and so on. In fact, we could even say when x equals pi n. Okay, so I build an f double prime sign chart, 0, pi, 2 pi, oh my god, this goes on forever. Uh-oh, in both directions. Well, I guess I shouldn't be surprised because I know cosine is vibrating, and this is just saying let's vibrate as we go uphill. That's why this function is always increasing, because of this sending us up, 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 and cosine is vibrating means we're going to have lots of changes in concavity. Okay, so if I plug in to my f double prime some things like pi over 2, I get a negative, and 3 pi over 2, I get a positive, and so I'm able to see that I have an inflection point here. Now, if I plug in 5 pi over 2 over here, sine of 5 pi over 2 is 1. That's negative 1. It keeps alternating. And so I can say that I have inflection points at x equals pi n because f double prime changes sign at those points. Okay? And increasing, I mean, concave up here and here. And so I could write some sort of general rule, but more likely what's going to happen is that they're going to give me some kind of this. But if they give me this kind of this, and I can restrict and say, okay, f is concave down on 0 to pi, and f is concave up on pi to 2 pi, and there's that inflection point at pi, that's all great and well and good, except now, because I put those boundaries on, now I've got maxes and mins, right? Because not only is the derivative never equal to 0 and the derivative is never undefined, but now I have endpoints. And whenever I have endpoints, I have to check. If my function is always increasing from here to here, I know that this is going to be a minimum and this is going to be a maximum. And I have to write my special justification sentences for endpoints. I will let you rewind this video or go back to the earlier part in this video where I explained how to write that sentence, but you really do need to be able to write that sentence. So that's kind of where we are and what we're doing now. We're going to be doing a lot of maxes, mins, increasing, decreasing, concave up, concave down, inflection points, but please don't forget the second derivative test. And when do I do it? Whenever I have y's in my derivative. If I have y's showing up in my derivative because I did some implicit differentiation, that's going to be a signal that I need to use the second derivative test, the one to use maxes to find maxes and mins. Okay, well, I hope this was helpful, and I look forward to taking your questions. Take care.